This is Algebra 2, Lesson 4-8, Complex Numbers. Now, when we learn to count, use the natural number system. As you've gotten older and learned more material, the number systems used have included other types of numbers. You've used the real number system, which includes both rational and irrational numbers, like pi being an irrational number. Now we will expand our number system to include numbers such as the square root of -2. An imaginary unit, otherwise known as I. Notice the I is written as a script I. It's defined as a number whose square is -1. So I squared equals -1, and I equals the square root of -1. If you put that in your calculator, and your calculator is on the real number system, it will always tell you you have an error. In order to get it to tell you that I equals the square root of -1 or that the square root of -1 equals I, it has to be in the complex number system. The imaginary number, an imaginary number is any number in the form of a plus bi, where b cannot equal 0. Complex numbers are imaginary numbers and real numbers together, a plus bi, where a is the real part and bi is the imaginary part. Like you might have something like, for example, 2 plus 3i. The 2 is the real part and the 3i is the imaginary part. The complex number plane is a way to represent a complex number graphically, where the horizontal axis is the real axis and the vertical axis is the imaginary axis. You would graph 3 minus 4i the same way you would graph 3 negative 4 on the coordinate plane. You would just have 3 on the x-axis and -4 would be on the imaginary axis. The absolute value of a complex number is its distance from the origin on the complex number plane. You find the absolute value by using the Pythagorean theorem. In general, the absolute value of a plus bi is equal to the square root of a squared plus b squared. Complex conjugates are number pairs in the form of a plus bi and a minus bi. Now, this is a lot of vocabulary thrown at you at once, but we're going to kind of go over most of this as we go through the lesson. The square root of a negative real number. For any positive real number a, the square root of negative a is -1 times a. The square root of -1 times a can be separated as the square root of -1 times the square root of a. So here, this is equal to this. This can be broken up to the square root of -1 times the square root of a. The square root of -1 is I, so you get I square roots of a. For example, if I have the square root of -4, that's I square roots of 4, because -1 times the square root of 4 and -1 is I. So the square root of 4 is 2, so that would be I times 2, so that becomes 2I. Note that the square root of -4 quantity squared is I square roots of 4 squared, which is I squared times the square root of 4 squared, which makes it -1 times 4, which makes it -4, not 4. Because remember, if the square root of -1 equals I, okay, I squared is equal to -1. So I acts like a real number in many respects. Square roots of all negative numbers can then be expressed as a product of I and a real number. I to the first is I. I squared is -1. So I to the third would become I squared times I. Well, I squared is -1, so that becomes -I. I to the fourth becomes I squared times I squared, which is -1 times -1, which just becomes 1. I to the 13th, then, would be like saying I squared taken to the 6th power. So I to the 13th becomes I squared raised to the 6th power. I squared is -1 raised to the 6th power. So it's so it's going to be equals -1 raised to the 6th power, which is I. So you end up getting just I. Okay, because -1 raised to the 6th power is 1. Okay, because we have this makes it to the 13th power. So I to the 20th is I squared to the 10th power. Notice you always use I squared and then take it to an even numbered power or an odd numbered power. If it's an even numbered power, you end up with I. Okay? Or you end up with 1. If it's an odd number of power, you're going to end up with -I, or you're going to end up with -1. Look at the pattern. It'll make sense. Okay, simplifying numbers using I. We're going to simplify each number by using the imaginary number I. So the square root of negative 2 is the same thing as saying the square root of negative 1 times the square root of 2. Okay? Square root of negative 1 is I, so this becomes I squared to 2. Okay? The square root of negative 12 becomes the square root of negative 1 times the square root of 12. 12 breaks down to 2 times 6, which is 2 times 3, so that would be 2 square roots of 3. Excuse me, negative 1. Negative 1 becomes I, so you have 2 times I square roots of 3. Okay, negative square root of 36 is negative square root of negative 1 times the square root of 36. Well, the square root of 36 is 6. The square root of negative 1 is I, so this is I times 6, or 6I. You always put the number before the I. Kind of acts like a variable, like 6x. You wouldn't put x6, you'd put 6x. Negative 54 is the square root of negative 1 times the square root of 54. 54 is 6 times 9. 6 is 2 times 3. 9 is 3 times 3, so the 9 would be 3 square roots of 6, and the negative 1 becomes an I, so this becomes 3I square roots of 6. Just a matter of breaking it down step by step. Now, a complex number can be written in the form of a plus bi, where a and b are real numbers, including 0. So a plus bi, a is your real part, bi is the imaginary part. Like I said before, that's the same thing as saying like 3 plus 5i. In the complex number plane, the point a comma b represents the complex number a plus bi. To graph a complex number, you locate the real part on the horizontal axis and you locate the imaginary part on the vertical axis. The absolute value of a complex number is its distance from the origin in the complex plane, and that is found by taking the square root of a squared plus b squared. So, if we were to graph the following numbers on the coordinate plane, okay, we're going to graph, it says what are the graph and the absolute value of each number, and I'm just going to move these up here so it's a little easier to use. So we're going to do 5 minus I, number 2 is going to be negative 3 minus 2I, and I'll put number 3 on there in a minute. So 5 minus I, remember, this is my real axis, this is my imaginary axis. Okay, so 5 minus I means I'm going to go to the right 5 units, 1, 2, 3, 4, 5. Minus I means minus 1I, so I'm going to go down 1 in the imaginary axis. And that happens to be problem number 1, that's 5 minus I. Okay. Number 2 says negative 3 minus 2I. I'm going to do this first, and then I'm going to do the absolute value of it. Okay. So, if we graph negative 3 minus 2I. Basically, I'm graphing negative 3, negative 2, so left 3, down 2, and this is negative 3 minus 2I. And problem number 3 here says we're supposed to graph 1 plus 4I. So basically, that's like graphing 1, 4. So right 1 up 4 is here, 1 plus 4I. Now, to find the absolute value of each one of these numbers, okay, you're just going to do the square root of a squared plus b squared. Okay? Square root of a squared plus b squared. Where a is your real part, b is the imaginary part, the number in front of the imaginary part. Notice you don't use the I. Okay? There's no I in this part of the formula. So this is going to be 5 squared plus 1 squared. Okay? Because the number in front for a is 5, the number in front of the I is 1. Okay, so 5 squared plus 1 squared, 25 plus 1 is 26, so this is the square root of 26. That's the absolute value of that number. Number 2 will be negative 3 squared plus 2 squared. Now, it doesn't really matter if they're negative or positive, because as you can clearly tell, that once you square it, it's going to be positive anyway. So this is going to be 9 plus 4. Which is a square root of 13. Number 3 here, we're going to have 1 squared plus 4 squared. So that's going to be 1 plus 16. So that's going to be the square root of 17. So that's how to graph those, and that's how to find the absolute value. Not a complicated system. Okay, so we did those three. Now, to add and subtract complex numbers, it's kind of like adding and subtracting regular numbers. With the regular numbers, you had to make sure you combine like terms. Here, basically, we're doing the same thing. We combine the real parts and we combine the imaginary parts separately. That's like your like terms. Real parts are one like term, imaginary parts are a different type of like term. If the sum of the two complex numbers is 0 or 0 plus 0i, then each number is the opposite or additive inverse of each other. The associative and commutative properties also apply to complex numbers just like they apply to real numbers. So if I have 8 plus 3i, and we're going to subtract from that 2 plus 4i, remember this subtraction sign means we run a negative through the entire parenthesis. So this becomes 8 plus 3i minus 2 minus 4i. Okay? And do what you have to do to make your i's look like i's and not ones. I kind of make them as script as I can so that they look more like i's and less like something really weird. Now I combine like terms. 8 is a like term to negative 2, so 8 minus 2 is 6, and 3i and negative 4i becomes negative I or negative 1i. Either one works. So I have 6 minus I or 6 minus 1i. Number 2, 7 minus 3 plus 2i. Run this negative through, so that becomes 7 minus 3 minus 2i. 7 minus 3 is 4 minus 2i. Combining your like terms. Real parts with real parts, imaginary parts with imaginary parts. 4 minus 6i plus 3i basically means 4 minus 6i plus 3i. Those are my common terms. Negative 6i plus 3i is negative 3i, so this becomes 4 minus 3i. That's the end of that page. For two imaginary numbers bi and ci, bi times ci becomes b times c times I squared, and I squared is negative 1, so it becomes b times c times negative 1, which becomes negative b times c. You can multiply two complex numbers in the form of a plus pi by using the procedure for multiplying binomials. In other words, distribute, or FOIL, however you want to think of it. So if I have 3i times 8i, okay, that's like saying 3 times 8 times I, which is 24i squared. I squared is negative 1, so this becomes negative 24. So let's simplify. If I have 12i times 7i, well, 12 times 7 times I times I. Right? 12 times 7 is 84, so this becomes 84i squared, but I squared is negative 1, so it becomes negative 1 times 84, or just negative 84. You'll get really good at remembering that I squared equals negative 1 really soon. Problem 2 here, we're going to have to use the distributive property, because I have a binomial times a binomial. So remember, it's the first number and everything times the second parentheses, so 6 parentheses 4 minus 3i, sign in the second number, minus 5i times 4 minus 3i, and I'm just going to distribute. Now when I distribute, I'm going to end up with 6 times 4 is 24. 6 times 3 is negative 18i. Negative 5 times 4, negative 5i times 4 is negative 20i. Negative 5i times negative 3i is positive 15i squared. Okay, so let's combine like terms what we know. This is 24 minus 38i plus 15i squared. But what is I squared? I squared is negative 1. So essentially, this becomes negative 15 because I squared is negative 1. So I have 24 minus 38i minus 15. 24 minus 15 happens to be 9, so this becomes 9 minus 38i. Number 3. Again, I'll need to distribute. So it's going to be, I'll use a different color, so if you use 3 parentheses 2 minus 4i, minus 7i, parentheses 2 minus 4i. So 3 times 2 is 6. 3 times negative 4i is negative 12i. Negative 7i times 2 is negative 14i. And negative 7 times negative 4 is positive 28i squared. So we have 6 minus 26i minus 28i because, excuse me, 28, not 28i, because I squared is negative 1, and negative 1 times positive 28 is negative 28. So 6 minus 28 is negative 22, so negative 22 minus 26i. It's just like multiplying binomials. If you weren't very good at multiplying binomials, you'll probably struggle a bit with multiplying complex numbers for the same reason. Okay. The product of complex conjugates is a real number. If I have a plus bi times a minus bi, they showed you how to do it with the formula. That becomes a squared minus 2ab plus b squared. What I'm going to do here is I'm just going to distribute it. A plus bi times a minus bi. So if I distribute, I'm going to have a parentheses a, minus bi, minus bi, plus bi times a minus bi. If I distribute that through, I'm going to have a squared minus abi plus, here I'm going to have abi if I put them in alphabetical order, abi minus b squared I squared. So the a squareds are fine. The negative abi and the positive abi cancel out. I squared is negative 1, so this becomes negative b squared times negative 1. So that becomes a squared plus b squared. So you'll see, okay, that should be a plus right here. Complex conjugate, that should be a plus right there. That should end up to be, yeah, a squared plus b squared. Make sure you change that on your notes. A squared plus b squared. Okay? So, when you work it out, you end up getting, when you multiply a plus bi times a minus bi, you end up getting a squared plus b squared. So once you recognize that, you could have something like 2 plus 3i times 2 minus 3i. My a term is 2 and my b term is 3. Remember, you leave the I out of it. And you're going to get a squared plus b squared, 2 squared plus 3 squared, which is going to be 4 plus 9, which is going to equal 13. That's a real number. Okay, so dividing complex numbers. Okay? You divide complex numbers similarly to dividing radicals. Because just like you can't have a square root in your denominator because it's not simplified, you can't have an I in the denominator either. It's the same basic principle because what is I? I is the square root of negative 1, which means that's putting a radical in your denominator, and you can't have a radical in your denominator. So, if I want to divide radical numbers, or complex numbers, I need to get my denominator to be a whole number, a real number. It can't have an I in it, so it can't be an imaginary number. So if 3 plus 4i is in my denominator, the only way I can get it to be a real number is to multiply it by a conjugate. The conjugate of 3 plus 4i is 3 minus 4i. So I'm going to multiply the top by 3 minus 4i and the bottom by 3 minus 4i. Remember, these are conjugates, 3 plus 4i and 3 minus 4i, so they basically become 3 squared plus 4 squared. So there's my denominator. My numerator, I'm going to have to multiply out by distributing. So that becomes, I'm going to make a nice long, that becomes 5 parentheses 3 minus 4i minus 2i parentheses 3 minus 4i. And now I'm going to actually do the math. So this would become 15 minus 20i minus 6i plus 8i squared all over 9 plus 16, which I will simplify in a minute. Okay, so now when I simplify this, I'm going to end up with, remember, I squared is negative 1, so this is essentially, okay, this 8i squared is actually negative 8. So 15 minus 8 is 7. So these like terms become 7 minus 26i all over 25. And it doesn't simplify any more than that because remember, we could rewrite this. This could be rewritten as 7/25 minus 26i over 25. It's the same thing. These are synonymous. This is a little easier to understand, but they mean the same thing. If we look at problem number 2, we have an I in the denominator, but we don't need to multiply it by a conjugate because there's no plus or minus sign. If there's a plus or minus sign between terms, then you have to multiply by a conjugate. I just have 6i. 6 is perfectly fine. I just can't have the I. So I need to multiply both the numerator and the denominator by I. So if I distribute that, I'm going to get 4i minus I squared over 6i squared. Well, I squared is negative 1, so that's going to be 4i minus 1, minus a negative 1, excuse me, minus a minus 1, over 6 times a negative 1, which is going to be 4i plus 1 over negative 6. Okay? Or 1 plus 4i, because we probably should put it in the complex conjugate form. So I'm going to put it in the complex conjugate form, 1 plus 4i over negative 6. Or if you prefer, you can move that negative to the numerator, and you'd get negative 1/6 minus 4i over 6, or 4/6i. Okay, and 4/6 would reduce to 2/3. So you could write this one more step. You could say that this is negative 1/6 minus 2/3 I. Any of these are perfectly acceptable. Okay? I don't have a preference to which way you write it, so any of those 3 ways would be acceptable. Probably my favorite way is this way, and then my next favorite way is this way. I prefer you reduce them if you can. All right, number 3 up here. 8 minus 7i over 8 plus 7i. So again, we have to multiply by a conjugate because I have a plus or minus sign between things. So my conjugate is going to be 8 minus 7i. I'm going to multiply the top and the bottom by 8 minus 7i. Remember, the conjugate means it's just a squared plus b squared, so that becomes 8 squared plus 7 squared on the bottom. But on the top, we're going to end up with 8 parentheses 8 minus 7i minus 7i parentheses 8 minus 7i. So distribute, you're going to get 64. 8 times 7 is 56 minus 56i minus 7i, oh, not 7, minus 56i again. 8 times 7, forgot to multiply it, 56i plus 49i squared. All over 64 plus 49. Simplifying. This becomes negative 49 because the I squared. 64 minus 49 is 15. Okay, so I will get 15 minus 56, and 56 is 112, 112i, all over 64 plus 49 is 113. And it doesn't simplify any further than that, so I'm done. Okay, now, lots of things you can do with complex numbers. Now we're going to factor with complex numbers. Okay, so if I have 5x squared plus 20, if I want to factor with this, I'm going to take a 5 out of there. And that'll leave me with x squared plus 4. Okay. So I know then that x squared plus 4, you might look at this and go, well, you can't factor that anymore. But here's the deal. How do I get to a 4? Remember, if this is a perfect square plus a perfect square, that's like saying a plus bi times a minus bi. So this becomes x plus 2i times x minus 2i, and of course you have to bring your 5 down. Because, how do I get to 4? 2i and 2i. Square root of 4 is 2. How do I get to get rid of the plus? I have to have an I into my equation. Okay. So before, remember when I said you can't factor the sum of a perfect square? You can't factor the sum of a perfect square into a real number solution. You can factor the sum of a perfect square into an imaginary number solution. So here, number 2, I'm looking at this, and the square root of 81 is 9. How do I get rid of the plus? I'm going to have an x plus 9i and an x minus 9i. Simple as that. And I'm done. That's the solution to that problem. That's the solution to the first problem. Last but not least, every quadratic equation has complex number solutions that sometimes are real numbers. So we can use the quadratic formula to solve equations, and you can still get imaginary number solutions in it. Remember when we said the discriminant? If you use the discriminant in lesson 4-7, we said if the discriminant was equal to 0, it's one real number solution. If the discriminant was greater than 0, okay, you had two real number solutions. If the discriminant was less than 0, you had two imaginary number solutions, or complex number solutions. Now we're going to deal with that. So what are the solutions of each equation? If I have 3x squared minus x plus 2 equals 0, if I'm going to solve this, I'm going to use the quadratic formula again because that's the easiest way to solve things. So a equals 3, b equals -1, and c equals 2. So negative b, negative 1 is positive 1, plus or minus the square root of b squared, -1 squared, minus 4 times a times c, all divided by 2a. Just like that. So you end up with 1 plus or minus the square root of -1 squared is 1. 1 minus 8 times 3 is 24, all over 6. So to simplify this, we're going to have 1 plus or minus the square root of -23 all over 6. Well, I can't leave it as the square root of -23. So remember, the square root of -23 is like saying I square roots of 23. So we have 1 plus or minus I square roots of 23 all over 6. And that's your complex number solution to a quadratic. Okay, that's your complex number solution to a quadratic. And last but not least, let's factor a different one. Or let's solve a different one. -x squared plus 4x minus 5. Okay. My a term is -1, my b term is 4, my c term is -5. So negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So -4 plus or minus the square root of 16 minus 20, because of -5 and -1 is +5. +5 times 4 is 20, all over -2. So -4 plus or minus the square root of -4 all over -2. We can simplify the square root of -4 because that's -4 plus or minus. Square root of -4 is 2i, because it's the square root of 4, which is 2, times the square root of -1, which is I. So we have -4 plus or minus 2i all over 2. Okay, now this can simplify. Okay, this can simplify because the way it's written, if we separated it, you'd have -4 over 2 plus or minus 2i over 2, which when you simplify that becomes -2 plus or minus I. And yes, you have to simplify it all the way down to its simplest form, which is the last thing that I wrote. Okay, complex numbers allow us to deal with problems that have imaginary number solutions. You might say, why in the world do we need an imaginary number system? We use an imaginary number system in a lot of things that we do for programming, especially with mechanics and engineering. So it has its uses. I don't use it much other than teaching math because I teach math. But it has its applications outside of just the math classroom.